Let's look at the molecular orbital diagrams of homonuclear diatomic molecules. In this particular video, like H2 or ions also like H2 plus, He2, which is diatomic. Yeah, homonuclear diatomic means it is made up of two atoms. That means this He2 molecule or H2 molecule is made up of two atoms, two hydrogen atoms. Homonuclear, they are of similar type. The combining atoms are of the similar type, so we are calling it as homonuclear diatomic molecules. Okay, we'll look at the molecular orbital configuration. So in this video of H2, H2 plus, He2 and He2 plus one by one. Let's first look at the molecular orbital energy diagram for hydrogen. Yes, the hydrogen is made up of two hydrogen atoms. Like this H2 molecule is made up of two hydrogen atoms. So each consisting of a single electron. So the configuration of each hydrogen atom is 1s1. Right? So the combination, that means a linear combination of these atomic orbitals, or by LCO methods, is atomic orbitals combined, that is 1s orbitals combined, resulting in the formation of one antibonding molecular orbital. And bonding molecular orbital. This is BMO. Right, one second. This is bonding molecular orbital and one antibonding molecular orbital. Right? Bonding molecular orbital is of lower energy and anti-bonding molecular orbital is of higher energy when compared to that of the energy of these atomic orbitals, that means of hydrogen atoms. Right. So this is represented by sigma and this is represented by sigma star. Right. So when we come to the filling up of the electrons in these two orbitals, that's the molecular orbitals, here each atom is contributing one electron each. So the two electrons first will enter into the bonding molecular orbital, that is sigma, here sigma 1s and sigma star 1s. These two are the molecular orbitals which are being formed by the combination of two 1s orbitals of two hydrogen atoms. Sigma 1s first gets filled up according to the Hoffer principle, which says that the lower energy orbitals gets filled up first. So now since the bonding molecular orbital is lower in energy, the two electrons will occupy this bonding molecular orbital. So what is the configuration of this now? How can I write the configuration of this? Simple, right? See, this is sigma 1s and there are two electrons in the bonding molecular orbital and 2. This is how you represent the electronic configuration of hydrogen atom. Right. Then how to calculate the bond order? See, let's calculate the bond order of this hydrogen molecule. So we know the formula of bond order is equal to half into number of electrons in the bonding molecular orbital minus the number of electrons in the antibonding molecular orbital. So number of electrons in the bonding molecular orbital is 2 and number of electrons in the anti-molecular orbital is 0. So half into 2 is equal to 1. So bond order is 2. That means the number of the covalent bonds formed in between the two hydrogen atoms is 1. That is why the bond order is 1 here. Right? This is how you explain the formation of the hydrogen molecule according to the molecular orbital theory, and this is the molecular orbital energy diagram for this H2 molecule. And what about the magnetism? Yes, since there is no unpaired electrons we can see here, so the two electrons which are present in the bonding molecular orbital are paired up and there is no unpaired electrons, so it is diamagnetic in nature. So we can explain the bond order and magnetic properties based on the filling up of these electrons. And let's look at this energy level diagram for H2 plus. Yes, this is H2 plus, where here the hydrogen atom and other one is a proton. So we have here one proton, one electron, here one proton. So the total of two protons and one electron and two atoms. Right here. So the hydrogen atom will contribute one electron and H plus no electrons, and by linear combination of atomic orbitals of these two atoms will get two molecular orbitals, that is lower in energy, that's bonding molecular orbital, and one is anti-bonding molecular orbital, where they're represented by sigma 1s and sigma star 1s. So the one electron which is contributed by one of the H atoms gets into the lower energy orbital, that is bonding molecular orbital. And how do you represent the electronic configuration? Sigma 1s and the one electron which is in the bonding molecular orbital, write it as a superscript. That's it. Right? This is electronic configuration. Right. How do you calculate the bond order? In bond order, you actually know the formula, number of the electrons in half into the number of electrons in bonding molecular orbital minus the number of electrons in the anti-bonding molecular orbital. So half into only one electron in this. So 0 electrons here. So half into 1 is half. So it's a fractional bond order. So the bond order is half here. Right, since there is one unpaired electron, we can see that it is paramagnetic in nature because number of unpaired electrons is 1. Right, so this is how you explain the bond order and the paramagnetism of H2 plus molecule. And when we compare the stability of this H2 plus, yes, since the bond order is half here, it is definitely more stable than either of the atoms, that is hydrogen as atom when it is isolated, or the proton. It is definitely more stable than the hydrogen atom or proton because it has some bond order, that is half. And we compare the bond length here of H2, yeah. When we compare the bond length of H2 and H2 plus, here the bond order is 1, here the bond order is half here. So bond order is inversely proportional to the bond length, right? So we have dealt with this in my previous video where bond order is inversely proportional to the bond length here. So the less the bond order, the more the bond length here. So here this is way more and this is less. That's the bond length here. This is the bond order. End of the slides. I mean, I've made a slide on this also. We'll check it out during the end of it. Yeah, this is what I explained in this one. So the bond order is greater than 0, that is half. H2 plus is more stable than isolated H atom and a proton. Right. So bond order of half here. So should be weaker than in H2 molecule. That is why the HH bond will be longer in H2 plus when compared to that of the hydrogen molecule. Right. So when we come to the He2 molecule, yes. So He, what is electronic configuration of this? There are 2 electrons in the s orbital, that is 1s2. And the 2 He atoms, that is 1s orbital of this overlap with the 1s orbital, that means linear combination of the atomic orbitals again results in the formation of 2 molecular orbitals, that is sigma and sigma star, bonding molecular orbital and anti-bonding molecular orbital, right? Represented by sigma and sigma star. Yes, so the 2 electrons and 2 electrons gets filled up here. The first 2 electrons will enter into the bonding molecular orbitals and the next 2 electrons will enter into the anti-bonding molecular orbitals. Right? Now, what about the bond order? Yes, the bond order is half into the number of electrons 2 minus 2, that is 0. The bond order is 0, which means the molecule does not exist at all. So the energy, the stabilization energy which is gaining by the entering of electrons into the bonding molecular orbital is cancelled by the energy which is increased by the electrons entering into the anti-bonding molecular orbital. Right? So the molecule does not exist at all. And what about He2 plus? Right. He2 plus, there are 2 He atoms, one He and He plus ion, and 2 electrons in one of the atoms, and there is 1 electron in He plus ion. The total of how many electrons? 2 electrons and 1 electron, total of 3 electrons, and 2 He atoms and 3 electrons. Right. So the 2 1s orbitals, the linear combination of atomic orbitals will get again 2 molecular orbitals, that is bonding molecular orbital and anti-bonding molecular orbitals, represented by sigma and sigma star. So that out of 3 electrons, the 2 electrons first enter into the lower energy orbital, that is sigma 1s, and next it will enter that one electron which is remaining will enter into the sigma star. So how do you represent the configuration of this sigma 1s, two electrons, that is a superscript on this, and sigma star 1s 1. This is bonding and this is anti-bonding. So this is electronic configuration of He2 plus. Right. When we calculate the bond order of this, half into the number of electrons in the bonding molecular orbital minus the number of electrons in the anti-bonding molecular orbital. So what are the number of electrons in the bonding molecular orbital? 2. Number of electrons in the anti-bonding, 1. So half into 1 is equal to half. So the bond order is half here. So the molecule do exist and it is more stable than either of the He atom or He plus. So, and what about the magnetism? It is, since there is one unpaired electron, we can see here, so that is paramagnetic in nature. So when we come to the molecular characteristics, or like bond order, bond length, and bond dissociation energy of different diatomic molecules and its ions, the simple diatomic molecules, let's look at it. For H2 plus, the electronic configuration is sigma 1s1. Bond order is half, and H2 it is 1s2, bond order is 1, He2 plus sigma 1s2 and sigma star 1s1, bond order is half, and He2 sigma 1s2, sigma star 1s2, the bond order is 0, so this molecule does not exist at all and the rest of the properties cannot be studied, right? So yes, for these three, when the bond order is half here, we can see the bond length is 106 and bond energy is 269. But if it is 1, when it is 1 here, the bond energy is more, 36. Right, bond order is directly proportional to the bond energy and inversely proportional to the bond length. So we have studied this in my previous video while doing with this molecular characteristics. So when it is one bond order, definitely the bond energy will be more when compared to that of this when it is bond order is less, because bond order is directly proportional to the bond energy. And when bond order is 1, the bond length is 74, it's less here, and when compared to that of the H2 plus when it's 106. So this is about the molecular orbital energy diagrams for diatomic molecules, H2 and He2 and their ions. Yes, if you like my video, please do like, share, and subscribe my channel. The whole chapter of this chemical bonding has been described on my YouTube channel. The details of the playlist has been given in the description box. You can go through it.